Right now, high on a mountain in Chile, a camera the size of a small car is waking up. It has 3 billion pixels. It can see things our eyes never will. And every 3 nights, it will photograph the entire sky above us. Every galaxy, every wandering asteroid, every flash of dying light. This is the Vera Rubin Observatory, and it is about to change everything we thought we knew about the universe. Tonight, we are going to visit a telescope that hunts invisible matter, catches exploding stars, and watches for rocks that could end life on Earth. If you enjoy this journey, a like and subscribe would mean a lot. Now, take a breath. We begin. Imagine you could freeze the sky. Every star, every distant glow, every faint smudge of light, all captured in a single photograph. Now imagine doing that again 3 nights later, and again, and again, for 10 straight years. That is exactly what the Vera Rubin Observatory is about to do. Sitting on a mountain almost 9,000 feet above sea level, in the dry desert of northern Chile, this telescope will scan the entire southern sky over and over, not once a year, not once a month, every 3 nights. Nothing like this has ever been attempted. Other telescopes point at one small patch of sky at a time. They stare deeply at a tiny sliver. Rubin does something different. It sweeps wide, it moves fast, and it sees faint things that other telescopes miss entirely. The result will be the most detailed time-lapse movie of the cosmos ever made. Stars that flicker, galaxies that drift, asteroids that tumble through the dark, explosions that bloom and vanish in days. All recorded, all catalogued, all searchable. Most telescopes are specialists. They zoom in on one object and study it for hours. That approach has given us incredible discoveries. But it also means the rest of the sky goes unwatched. Things happen out there every single night that nobody sees. Stars explode, asteroids drift, flashes of light appear and disappear with no explanation. Rubin will be the first telescope to keep watch over everything, all at once, for an entire decade. It will photograph roughly 18,000 square degrees of sky. That is nearly half the entire celestial sphere, and it will do it with a level of detail that was impossible just a few years ago. Each photograph will be sharper, wider, and deeper than anything taken by any ground-based telescope before it. And it will keep doing it relentlessly, night after night, for 10 years straight. But here is what makes this truly strange. Most of what Rubin will study cannot be seen, not by human eyes, not by any camera. The telescope was built to chase something invisible, something that holds galaxies together and yet has never been directly observed. Scientists believe this invisible substance makes up the vast majority of all matter in the universe. It does not glow, it does not reflect. It simply exists, pulling on everything around it with gravity. And we still do not know what it is. We will get to that mystery soon. But first, we need to understand how a telescope this powerful came to exist. And that story starts with a woman who was told she did not belong in science. A woman who ignored every person who doubted her. A woman who looked where nobody else was looking and found something that rewrote the rules of the cosmos. What she found in the dark changed the universe forever. And the telescope that now carries her name will search deeper into that darkness than she ever dreamed possible. Vera Rubin was born in Philadelphia in 1928. By the age of 10, she was sketching the paths of stars from her bedroom window in Washington. Her father helped her build a telescope from spare parts. Her mother defended her long exposure photographs when photolabs thought the streaks of starlight were printing errors. She was curious, she was stubborn, and she was told, repeatedly, that astronomy was not a place for women. When she applied to Princeton for graduate school, she was rejected, not because of her grades, because Princeton did not accept women into its astronomy program. That policy stayed in place until 1975. Imagine that. One of the greatest astronomers of the 20th century was turned away simply because of who she was. Rubin went to Cornell instead, then Georgetown, then the Carnegie Institution in Washington, and there, alongside astronomer Kent Ford, she began studying how galaxies rotate. What they found made no sense. The stars at the outer edges of galaxies were moving just as fast as those near the center. According to everything physics predicted, those outer stars should have been slower. Much slower. Without enough gravity to hold them, they should have been flung into the void. But they were not flying apart. Something unseen was holding them in place. Something massive. Something everywhere. Something no telescope had ever detected. Vera Rubin had found the first solid evidence for dark matter. She and Ford used a special instrument called a spectrograph, one of the most sensitive ever built at the time, to measure the speed of stars in galaxy after galaxy. They worked at observatories in Arizona and beyond, collecting data over months and years. When Rubin finally sat down and sketched their findings on paper, the answer became clear. The galaxies were embedded in something invisible, something enormous. She studied more than 60 galaxies. Every single one showed the same pattern. The visible matter, the stars and gas, was not nearly enough to explain what was happening. There had to be something else, something invisible, and there had to be a lot of it. Scientists now believe that dark matter makes up more than 80% of all the matter in the universe. And yet, decades later, we still do not know what it is. We cannot touch it, we cannot see it. We can only measure its pull. It is the most abundant substance in the cosmos, and it remains one of the deepest mysteries in all of science. Vera Rubin never received a Nobel Prize. Many believe she was overlooked because of her gender. Others call it one of the greatest omissions in the history of the award. She died in 2016, at the age of 88. But her name now sits on the most ambitious telescope ever built, a telescope that will hunt the very thing she spent her life proving was real. And that telescope is about to finish what she started. Here is a fact that should keep you awake at night. Everything you have ever seen, everything you have ever touched, every star, every planet, every grain of sand, makes up only about 5% of the universe. 5%. The rest is invisible. Roughly 27% is dark matter. It does not glow. It does not reflect. It does not absorb light. It simply pulls on things with gravity. We know it is there because without it, galaxies would fly apart. Stars would scatter. The large-scale structure of the cosmos would not exist. Every galaxy you have ever seen in a photograph is held together by something you will never see. And the remaining 68% is something even stranger: dark energy. Dark energy is the name scientists give to whatever is causing the universe to expand faster and faster. Gravity should be pulling everything back together. Instead, galaxies are racing away from each other at increasing speed. Something is pushing, something enormous, and nobody knows what it is. Nobody has even come close to a definitive answer. Think about that for a moment. The gap in our knowledge is not some minor detail. It is almost the entire universe. We are living inside a cosmos that is 95% mystery. The atoms that make up your body, the ground beneath your feet, the air you breathe, all of that is a tiny fraction of what actually exists. We are the exception. The invisible is the rule. Confirmed. Dark matter exists. We can measure its effects on galaxies, on the bending of light, on the structure of the universe itself. It has been confirmed through decades of observation by hundreds of independent research teams. Theory: dark matter might be a new type of particle we have never detected. Experiments deep underground, in mines and tunnels shielded from cosmic rays, are searching for it right now. So far, nothing has been caught. Unknown. What dark energy actually is, and whether it has been the same strength across all of time. It could be constant. It could be changing. It could be something entirely beyond our current physics. We simply do not know yet. The Vera Rubin Observatory was designed specifically to attack these questions. Its camera, its mirrors, its software, everything about it was built to study the invisible. Every part of the telescope was shaped by one goal: see what cannot be seen, measure what cannot be touched, map what cannot be photographed directly. By watching how billions of galaxies move, how their light bends, and how the structure of the cosmos changes over time, Rubin will build the most detailed map of dark matter ever created. And it may finally give us clues about dark energy. Clues that could reshape our understanding of reality itself. But to do that, it needed the most extraordinary camera ever built. And that is where this story takes a turn nobody expected. Most cameras fit in your hand. Some fit in your pocket. The camera inside the Vera Rubin Observatory weighs more than 6,600 pounds. It is roughly the size of a small car, and it contains the largest digital sensor ever built for astronomy, 3.2 billion pixels. That is 3,200 megapixels. To put that in perspective, a modern phone camera has about 12 megapixels. You would need roughly 260 phones lined up, sensor to sensor, to match what this one camera captures in a single shot. Each image covers a patch of sky 45 times the area of the full moon, and a new image is taken every 40 seconds. Think about that for a moment. A camera this massive, this sensitive, firing off a new photograph faster than most people can brush their teeth. The sensor is not a single chip. It is a mosaic of 189 individual detectors, carefully arranged into a flat surface about 2 feet across. Each detector is a charge-coupled device, a piece of silicon that converts photons of light into electrical signals. Together, they create an image so detailed that a single exposure could fill around 1,500 high-definition television screens. Now, here is where it gets even more interesting. The camera can see light that your eyes cannot. It works across 6 different color filters, from ultraviolet to infrared. By switching between these filters, it captures the universe in wavelengths that reveal hidden details. Dust clouds that block visible light become transparent. Distant galaxies shift their color as their light stretches across billions of years. The filters themselves are enormous. Each one is about 30 inches across. They sit in a carousel inside the camera, and a machine swaps them during observations. 5 can be loaded at once. The 6th waits in a special storage bay nearby. On any given night, the telescope can observe in 5 different colors of light, switching between them as needed. The sensors also need to be kept extremely cold to work properly. A cooling system called a cryostat maintains the temperature deep below freezing night after night, year after year. If the temperature drifts even slightly, the images become noisy and unreliable, so the cooling system must be perfect for a full decade. That means 10 years of continuous, precise temperature control on a mountaintop in the Chilean Andes, where conditions outside the dome change constantly. The entire camera is a marvel of coordination. Optics, electronics, cooling, filters, and data systems all working together inside a single instrument. Nothing this complex has ever been built for astronomy before. Every subsystem had to work flawlessly with every other subsystem in conditions that would test the limits of engineering. Building this camera took nearly 2 decades. Hundreds of scientists and engineers across the globe worked on its design, fabrication, and testing. But building it was only half the challenge. Getting it to Chile was another story entirely. The idea for this telescope was first discussed in the late 1990s. Back then, it was called the Large Synoptic Survey Telescope. The concept was simple in theory, but staggering in practice. Build a telescope that can survey the entire visible sky repeatedly for a decade. By 2001, it was officially proposed. By 2007, construction of the primary mirror had begun, funded by private donations. Two technology billionaires, Charles Simonyi and Bill Gates, contributed $30 million combined. That early money kept the dream alive when government funding had not yet arrived. The camera itself was designed and built at the Stanford Linear Accelerator Center in California, a national laboratory run by Stanford University. Construction on the camera started in 2015. Teams from national laboratories and universities across the country contributed components. Each piece had to meet extraordinary standards of precision. The sensor array came from Brookhaven National Laboratory in New York. Scientists there developed a new kind of light sensor, more sensitive and faster than anything used in astronomy before. The lenses were ground to extreme precision. The cryostat, a cooling system that keeps the sensors at incredibly low temperatures, had to maintain stable conditions night after night, year after year, for a full decade of operation. By 2018, the cryostat was complete and 12 of the 21 sensor rafts had been delivered. By 2021, all 6 filters were finished. By late 2021, the entire camera had been cooled to operating temperature for the first time. Engineers watched the readouts carefully. Everything had to work together in perfect harmony. Then came years of final testing, checking every sensor, verifying every connection, running simulations of what the camera would face on the mountain, vibrations from wind, temperature swings between day and night, the relentless pace of taking a new image every 40 seconds for 10 years straight. Every possible failure mode was tested and planned for. Every weak point was identified and reinforced. The total construction cost of the observatory came to roughly $680 million. Decades of planning, billions of calculations, thousands of people from more than 40 countries, all converging toward a single goal: building a machine that could see the invisible, a telescope designed not to look at one thing, but at everything, a device that would photograph the cosmos with a patience and precision no human could match. Then came the moment everyone had been waiting for. In April of 2024, the camera was declared complete. It had passed every test. It was ready, but it was sitting in a clean room in California. The telescope was waiting in Chile, on a mountain more than 5,000 miles away. How do you move something this fragile across half a continent, over winding mountain roads, to one of the most remote observatories on Earth? Very, very carefully. And even then, the team held its breath the entire way. When the camera was ready to leave California, engineers faced a problem that no shipping company had ever solved before. They were not moving ordinary equipment. They were transporting the most sensitive optical instrument ever constructed, packed with delicate silicon sensors, precision lenses, and components that could be ruined by a single hard bump. There was no backup camera. There was no second copy sitting in storage. 2 decades of work and hundreds of millions of dollars were packed into one container. If anything went wrong during transport, the entire project could be set back by years. The journey began at the Stanford Linear Accelerator Center, where the camera was sealed inside a custom-built container designed to absorb vibrations. The container was engineered to protect against shocks, temperature changes, and humidity. It was loaded onto a truck outfitted with advanced suspension systems. Every mile of the route was mapped in advance. Every bump in the road was catalogued. Every bridge was checked for weight limits. The camera traveled by ground to a nearby airport, then by cargo plane to Chile. Once on the ground in South America, it was loaded onto another specially prepared vehicle for the final leg. The road to the observatory climbs nearly 9,000 feet into the Chilean Andes. It twists through mountain passes. It narrows along cliffs, and it is not forgiving. Engineers monitored vibrations in real time during the entire trip. Sensors inside the container tracked every jolt, every sway, every bump. If the readings exceeded safe limits, the convoy would stop. There would be no rushing. When it arrived safely at the summit, the team breathed again. The camera had survived. But the hardest part was still ahead. In early March of 2025, the camera was lifted into position on the telescope. Workers used a vertical platform to raise the 6,600-pound instrument into the telescope structure, aligning it with absolute precision. Every millimeter mattered. A misalignment of even a fraction of an inch would degrade the images beyond what the science required. The camera now sits at the center of the optical system, between a massive primary mirror and a secondary mirror. Together, they form a light-gathering machine unlike anything else on Earth. Confirmed, the camera was installed successfully in March of 2025, and within weeks, it began seeing the sky for the very first time. Light from distant stars passed through the mirrors, through the filters, and onto the sensors. The pixels lit up, the data flowed. After 2 decades of planning, building, and waiting, the eye of the telescope finally opened. The team watched the first photons arrive on their screens. Years of effort, condensed into a single moment of light. For many of them, it was the culmination of an entire career. Some had been working on this project since they were graduate students. Now, finally, the camera was alive. But the mountain it sits on is just as remarkable as the camera itself. Not every mountain is good for astronomy. You need height to get above as much of the atmosphere as possible. You need dry air because water vapor blurs starlight, and you need stillness. Turbulence in the air smears images and turns sharp points of light into fuzzy blobs. The Vera Rubin Observatory sits on Cerro Pachon, a peak in the Coquimbo region of northern Chile. The summit rises about 8,800 feet above sea level. The Atacama Desert stretches nearby, one of the driest places on Earth. Some weather stations in the Atacama have never recorded a single drop of rain. The air is so dry that moisture barely exists at these altitudes. Chile is home to some of the greatest observatories in the world for exactly this reason. The Gemini South Telescope and the Southern Astrophysical Research Telescope both sit on the same mountain as Rubin. A few peaks away, the European Southern Observatory runs telescopes that have been making discoveries for decades. This small stretch of Chilean mountains has become the astronomy capital of the planet. The air above Cerro Pachon is remarkably stable. On a good night, the seeing conditions allow the telescope to resolve incredibly fine details. Stars appear as tight, clean points of light rather than smeared disks. This stability is not just useful, it is essential. Without it, the camera's 3 billion pixels would be wasted on blurry images. The observatory sits far from any major city. Light pollution, the glow from streetlights and buildings that washes out faint stars, is almost non-existent here. The sky above the observatory is among the darkest on Earth. On a clear night, the Milky Way blazes across the sky with a brilliance that most people alive today have never seen. The darkness is not a limitation here. It is the entire point. This is a place where the universe can be seen as it truly is, undimmed, unfiltered, vast and ancient and blazing with light that has traveled for billions of years to reach this mountain. The base facility is located about 60 miles away in the city of La Serena. Data flows from the summit down the mountain through high-speed fiber optic cables, then across the ocean to data centers in the United States and France. Every single night, the telescope will generate roughly 20 terabytes of raw data. Over 10 years, the total will reach hundreds of petabytes. That is more astronomical data than every other observatory in history, combined, has ever collected. Confirmed. Rubin will gather more data per year than all previous sky surveys put together. The information flowing off this mountain every night would fill thousands of hard drives. Processing it requires supercomputers. Storing it requires data centers on 2 continents, and analyzing it will keep scientists busy for generations. And all of that data starts with one thing, a mirror shaped in a way no one had tried before. What makes this mirror different changes everything. Most large telescopes use two mirrors, a big primary mirror to collect light, and a smaller secondary mirror to redirect it toward the camera. Rubin uses three, but here is the twist. Two of those mirrors are carved from the same piece of glass. The primary mirror and the tertiary mirror share a single blank of glass, a piece about 27 feet across. The outer ring acts as the primary, gathering light from the sky. The inner ring acts as the tertiary, redirecting light after it bounces off the secondary mirror above. Nobody had ever combined two mirrors into one piece of glass at this scale. It was a bold idea, and it worked. The secondary mirror hangs above, about 11.5 feet across. Together, the three mirrors work as a team, funneling light into the camera with extreme efficiency and covering an unusually wide field of view. That wide field is the key. Most research telescopes see a tiny area of sky, like looking through a drinking straw. They capture incredible detail, but only of a very small region. Rubin sees a patch 45 times the area of the full moon in every single exposure. That is how it can scan the entire southern sky in just 3 nights. But a wide field of view creates a problem. The edges of the image can become distorted. Stars near the corners stretch and blur. Colors shift. The three-mirror design corrects for this, keeping the image sharp from center to edge. Every corner of the frame is as crisp as the middle. That level of uniformity across such a wide field had never been achieved before. The mirror was cast at the University of Arizona, at a facility that spins molten glass inside a rotating furnace. As the glass hardens, centrifugal force shapes it into a curved dish. The raw mirror then went through years of careful grinding and polishing. Layer after layer of glass was removed, micron by micron, until the surface reached the exact curvature the design required. The precision is extraordinary. If the mirror were scaled up to the size of the continental United States, the tallest bump on the surface would be less than half an inch. That level of smoothness, at that scale, is almost beyond comprehension. It required new tools, new techniques, and extraordinary patience. Theory. This three-mirror system could inspire future telescope designs around the world. It proved that combining mirrors into a single piece of glass is not just possible, but practical for large-scale astronomy. Other projects are already studying the approach. What was once considered risky is now considered visionary. The mirrors, the camera, the filters, the software. Each piece is extraordinary on its own. Together, they form something greater. A machine built to do what no machine has ever done. But the mirror is just one piece of the puzzle. What matters most is what the telescope does with the light it captures, and the speed of that process is almost unbelievable. Here is something that sounds impossible. The Vera Rubin Observatory takes a brand new exposure of the sky every 40 seconds. Not every hour, not every few minutes. Every 40 seconds. That includes the time it takes to read out the data from the sensor, reposition the telescope to a new patch of sky, and start the next exposure. The actual exposure time for each image is about 30 seconds. The rest is overhead. The telescope swings to a new position, locks on, and fires again, over and over, all night long. This speed is built into every part of the observatory. The telescope is designed to slew quickly and settle fast, with minimal vibration. The camera reads out its 3 billion pixels in just 2 seconds. That alone is a remarkable achievement. Most astronomical cameras take much longer to process their data. The data pipeline begins processing the image almost instantly, before the next exposure is even complete. Why does speed matter so much? Because the universe is full of things that change. A star might brighten suddenly, signaling a supernova. An asteroid might drift across the field, revealing its orbit. A flash of light might appear and vanish within hours, leaving behind a mystery that nobody can explain. If you only photograph the sky once a week, you miss these events. You see the before and the after, but not the moment itself. Rubin is designed to catch the moment, the exact instant something changes. Over the course of a single night, the telescope will take around 800 individual images. Each one covers a different patch of sky. Stitched together over 3 nights, they form a complete map of the visible southern hemisphere. Then it starts again, another sweep, another map. Compared to the previous one, pixel by pixel, anything that moved, anything that brightened, anything that vanished, gets flagged. The software behind this comparison is remarkably sophisticated. It does not just check if a pixel got brighter, it checks the shape of the brightness, the color, the rate of change. It compares against catalogs of known objects. It filters out satellites, cosmic rays, and camera artifacts. It separates real cosmic events from noise, glitches, and reflections. What remains are real changes in the sky, real events, real discoveries waiting to be understood. This entire process runs automatically. No human sits at a screen watching pixels change. The software does the watching. It never gets tired, it never blinks, and it processes the flood of data faster than any team of astronomers could hope to match. By the time a human could blink, the system has already classified the change and decided whether the world needs to know about it. Confirmed. The system will generate around 100,000 alerts every single night. Each alert is a question. Something changed. Something happened. What was it? Some of those questions already have answers. But what astronomers found in the very first test images stunned everyone. On June 23, 2025, the Vera Rubin Observatory revealed its first images to the world. They called it the First Look event. It was held at the National Academy of Sciences in Washington. Astronomers, engineers, journalists, and space enthusiasts gathered to see what the telescope had captured, and the images took their breath away. In just over 7 hours of observing time, the telescope captured 678 separate images. When combined, they revealed details that would normally take other telescopes weeks to see. Faint nebulae glowed with impossible clarity. Distant galaxies, thousands of them, appeared where the sky had looked empty before. The Trifid Nebula and the Lagoon Nebula, clouds of gas and dust several thousand light-years away, were revealed with stunning detail. Structures within the clouds, filaments of hydrogen lit by young stars, stood out as if painted on glass. Colors shifted from deep blue to warm orange across the field, each shade representing a different temperature, a different chemical, a different chapter in the life of the cloud. But the team was not just looking at pretty pictures, they were testing the entire system. Could the camera deliver the sharpness they needed? Could the data pipeline handle the flood of information? Could the telescope move fast enough to keep its schedule? Could the filters swap without error? The answer, across the board, was yes. Every system performed as designed. Some performed better than expected. The telescope moved smoothly. The filters swapped cleanly. The data pipeline kept up with the flood. Engineers who had spent years worrying about what might go wrong watched as everything went right, and buried in those first test images were surprises that no one had planned for. Hidden among the nebulae and galaxies, tucked into the background like uninvited guests, were objects that nobody knew existed. Among the thousands of objects detected in that early data, roughly 1,900 asteroids had never been catalogued before. They were brand new discoveries, found accidentally in a camera that had barely started working. Nobody told the telescope to look for asteroids during that test. It simply saw them. They were there, drifting through the background, and the software picked them out automatically. For a telescope still in its commissioning phase, still being fine-tuned, this was an extraordinary result. The engineers were testing the plumbing, and gold came pouring out of the faucet. Nobody had expected real scientific discoveries this early. The telescope was supposed to be in warm-up mode, calibrating sensors and adjusting focus. Instead, it was already finding things nobody had ever seen. The astronomical community took notice. If the telescope could produce results like this during testing, what would happen when the full 10-year survey began? The answer was both thrilling and humbling. Nobody knew for certain, but everyone knew it would be big. But when scientists looked more closely at those asteroids, one of them turned out to be doing something no one expected. It was spinning, faster than anything its size had ever spun before. Among those first test observations, scientists found roughly 1,900 asteroids that had never been seen before. Not in any database, not by any telescope. They were hiding in plain sight, drifting quietly through the dark until the camera caught them. This happened during the commissioning phase, before the official 10-year survey had even begun. The telescope was still being calibrated. The team was running tests. And yet, in just about 10 hours of observing spread across 7 nights in April and May of 2025, almost 2,000 unknown objects emerged from the data. Some of them were close. Some were far out in the main asteroid belt between Mars and Jupiter. Each one was moving, following its own orbit, tracing a path it had followed for billions of years without anyone noticing. They had always been there. We just did not have eyes sharp enough to see them. What made these detections possible was the software. A system called HelioLIN-C, developed at the University of Washington, was designed specifically for this observatory. It can detect moving objects by linking together observations taken on different nights, even when the asteroid is faint and the motion is small. Traditional asteroid hunting requires at least 3 observations in a single night. HelioLIN-C can work with just 2 taken on separate nights. That makes it far more efficient and far more sensitive. This software will be the engine behind the observatory's solar system discoveries for the next decade. It was built to find things that are easy to miss, and in its very first real test, it delivered far beyond expectations. The team estimates that over the course of the full survey, the telescope could detect several million asteroids. That is 10 to 100 times more than we currently have in our catalogues. Our map of the solar system is about to get dramatically more detailed. Objects that have been drifting unseen for billions of years will finally have names, orbits, and stories. Many of these asteroids will be ordinary rocks following ordinary orbits, but some will be unusual. Some will have strange compositions, reflecting light in unexpected colors. Some will follow orbits that bring them uncomfortably close to Earth, and some will be spinning in ways that challenge what we thought we knew about how asteroids hold themselves together. Each discovery added a new dot to the map, a new object with a story stretching back billions of years. Some of these asteroids may contain water ice, some may be rich in metals, some may hold clues about the conditions that existed when the planets were forming. Every single one is a piece of the puzzle, a tiny fragment of the ancient story of how our solar system came to be. One asteroid in particular gave scientists something to talk about, and the reason was speed. What it was doing out there in the dark should have been impossible. Among the 19 rapidly rotating asteroids found in the observatory's early data, one stood out. Its designation is 2025 MN 45. It is about 4/10 of a mile across, roughly the length of 8 football fields, and it completes a full rotation every 1.88 minutes. That means this rock, spinning in the blackness of space, turns around faster than the minute hand on a clock. It is the fastest spinning asteroid of its size ever discovered, and the question it raises is simple. How? Because something that large should not be able to spin that fast without tearing itself apart. Most asteroids are not solid boulders. They are rubble piles, loose collections of rock and dust held together by gravity. Spin them too fast, and gravity cannot hold them. The pieces fly apart like mud off a spinning tire. For an asteroid in the main belt, the speed limit before breakup is roughly 1 full rotation every 2.2 hours. Anything faster, and the asteroid needs to be structurally strong. It needs internal cohesion. Something has to be physically holding it together beyond just gravity. 2025, MN45 spins more than 70 times faster than that limit. This means it cannot be a rubble pile. It is something more solid, more dense, more internally connected than scientists expected to find at that size. It could be a single chunk of metal and rock, forged in a collision billions of years ago and never broken apart since. Or it could be held together by forces we do not fully understand yet. Either way, its existence is a puzzle. A rock this big, spinning this fast, surviving in one piece. It should not be possible. And yet, there it is. The discovery was published in the Astrophysical Journal Letters. It was the very first peer-reviewed scientific paper to use data from this observatory's camera. The paper that launched a new era of astronomical discovery happened to be about a spinning rock the size of a small town, tumbling through the void at a speed that defies explanation. Confirmed, this is the fastest spinning asteroid over 500 meters in diameter ever found. The team also identified 18 other superfast rotators. Most of them live in the main asteroid belt, at distances where previous telescopes simply could not see them clearly. The observatory's enormous light collecting power made the difference. It sees fainter, farther, and faster than anything before it. Objects that would have been invisible to every previous survey now stand out clearly in the data. The deep space between Mars and Jupiter, once considered well mapped, is suddenly full of new surprises. The darkness is crowded with things we never knew were there. But speed is not the only thing scientists care about when it comes to asteroids. Some of them are headed our way, and finding them in time is a matter of survival. There are asteroids out there, right now, following orbits that cross Earth's path. They are called near-Earth objects. Most of them are small and harmless, but some are large enough to cause catastrophic damage if they ever hit us. An asteroid about 460 feet across could destroy an entire city. The blast would flatten everything for miles in every direction. 1/2 a mile wide could affect the global climate, throwing enough dust into the atmosphere to block a portion of incoming light for months. And anything larger than 6 miles could trigger an extinction-level event. We know this because it has happened before. 66 million years ago, an asteroid roughly 7.5 miles across struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons detonating at once. It killed about 75% of all species on Earth, including the dinosaurs. The world burned. Then it froze. Life nearly ended. Today, astronomers have catalogued most of the largest near-Earth objects. The ones big enough to end civilization have mostly been found. That is the good news. The bad news is that smaller ones, those between about 460 feet and 1/2 a mile, are harder to spot. They are faint, they move fast, and many of them remain completely unknown. The United States Congress has mandated that 90% of all near-Earth objects larger than 460 feet be identified and tracked. We are not there yet. As of today, a significant portion of these objects have not been found. They are out there, following their orbits in silence, and we have no idea where they are. The Vera Rubin Observatory could change that. Its wide field of view and sensitivity allow it to detect asteroids as small as 460 feet across, even out in the main belt. Depending on the survey strategy chosen, it could find between 60 and 90% of all potentially hazardous asteroids in that size range. For the first time, we would have a nearly complete inventory of the objects that could threaten our world. We would know where they are, how fast they move, and how much warning we would have. The difference between knowing about a threat and being blind to it could mean the difference between preparation and catastrophe. Every asteroid found is one fewer that can catch us by surprise, one fewer threat hiding in the dark. Theory. The observatory's data could also help predict future impacts with greater accuracy by refining the orbital paths of known objects. Every discovery is a step toward protection. Every new orbit calculated is a warning delivered early. But asteroids are not the only violent events this telescope will track. Far beyond our solar system, stars are dying in the most spectacular way imaginable. Catching those deaths in time has been nearly impossible, until now. Somewhere in the Milky Way, right now, a massive star is reaching the end of its life. Its core is collapsing. Layers of iron, silicon, and oxygen are crushing inward under the weight of gravity. The outer layers are about to be blown apart in an explosion so powerful that, for a brief moment, the dying star will outshine the entire galaxy. This is a supernova, and in a galaxy like ours, one happens roughly once or twice per century. The problem is, we keep missing them. The last core collapse supernova observed from Earth happened nearly 1,000 years ago. That means we have missed at least 10, maybe more. They exploded. They lit up regions of the sky, and nobody was watching the right patch at the right moment. The light came, it faded, and we never knew. Why do we miss them? Because the Milky Way is enormous, because dust blocks visible light in many directions, because supernovae appear without warning and fade within weeks, and because, until now, no single telescope could monitor the entire sky fast enough to catch one in the act. A supernova in our galaxy would be an extraordinary scientific event. It would release a flood of light across every wavelength, from radio to gamma rays. It would send out neutrinos, ghostly particles that pass through matter almost without interacting, and it would generate gravitational waves, ripples in the fabric of space itself. Studying all of those signals together, at the moment they arrive, would teach us more about how stars die than decades of theory ever could. Here is where it gets exciting. Neutrino detectors around the world can sense a supernova before the light reaches us. Neutrinos escape the collapsing core minutes to hours before the shockwave breaks through the surface. They travel at nearly the speed of light and pass through the star as if it were not there. They can serve as an early warning system. But once the alert goes out, someone has to find the explosion in the sky, quickly, before it fades. Confirmed, recent research shows that the Vera Rubin Observatory has between a 57 and 97% chance of catching the next galactic supernova based on where it occurs. No other telescope comes close to those odds. And because the telescope photographs the same areas repeatedly, it would have images of the region before the explosion, giving scientists a rare before and after comparison. A galactic supernova is one of the most anticipated events in modern astronomy. Entire careers have been built around preparing for one. Detector networks stand ready. Observation plans sit in drawers, waiting. All they need is the explosion. When it comes, the scientific community will mobilize faster than for any event in history. But supernovae are just one kind of cosmic explosion this telescope will chase. The universe is full of sudden, violent events that flare and vanish, and some of them have never been seen at all. The universe is not as calm as it looks. Things explode, things collide, things brighten in seconds and disappear in hours. These events are called transients, and they have been one of the hardest things to study in all of astronomy. The challenge is timing. A gamma-ray burst might last only a few seconds. Blink, and you miss it. A tidal disruption event, where a black hole tears a star apart piece by piece, might brighten over days and fade over weeks. A kilonova, the collision of two neutron stars, might glow for just a few nights before it dims forever. Each of these events carries enormous scientific value, and each one is almost impossible to predict. Traditional telescopes, which stare at one small piece of sky for hours, are terrible at catching these. By the time someone notices something unusual and points a telescope at it, the event may already be fading. The window closes. The moment is lost. Rubin changes this completely. Because it photographs the entire southern sky every 3 nights, it creates a built-in surveillance system for the cosmos. Anything that changes, anything that brightens, anything that appears where nothing was before, gets detected automatically. The software compares each new image to a reference image of the same patch of sky. If a pixel is brighter than expected, the system flags it. If a new dot of light appears where none existed, an alert goes out. The process is entirely automated. No human needs to spot the change. The computer finds it, classifies it, and sends the message. 100,000 alerts per night, each one a potential discovery, each one sent to astronomers around the world within 60 seconds. Some of those alerts will be familiar. Known variable stars that pulse in predictable rhythms, known asteroids crossing the field, satellites catching a glint of reflected light, but some will be entirely new. Flashes of light with no explanation, events that do not match any known category, phenomena that have never been documented before. Unknown. What classes of transient phenomena remain undiscovered? How many types of cosmic events are happening right now that we have never even imagined? This observatory might be the telescope that reveals them. Every night could bring the first detection of a phenomenon that has no name, no theory, no category, just a flash of light in a place where nothing should be flashing. The universe is stranger than we know, and the only way to learn just how strange is to keep watching, everywhere, all the time, for years. That is exactly what this telescope will do, and over 10 years, its record of the sky will become the most complete catalogue of cosmic violence ever assembled. But catching explosions is only part of the mission. The deeper goal, the one Vera Rubin herself would have cared about most, involves something far more mysterious: the invisible architecture of the universe itself. If you could see all the matter in the universe, not just the bright parts, you would see something incredible. A vast web of filaments stretching across billions of light years, connecting galaxies like beads on a string. Between the filaments, enormous empty voids, and at the intersections, massive clusters of galaxies pulled together by gravity into dense, glowing knots. This is called the cosmic web, and most of it is invisible. The galaxies we see are just the glowing nodes in a much larger structure. The filaments are made mostly of dark matter, threaded with gas so thin it barely registers on any instrument. The voids are not truly empty, but they are close. Regions of space stretching hundreds of millions of light years across, where almost nothing exists, just silence and darkness. We know the cosmic web is there because of computer simulations and indirect observations. When scientists model the universe from the Big Bang forward, feeding in what we know about gravity, dark matter, and the initial conditions of the cosmos, the dark matter naturally clumps into this web-like pattern. Galaxies form where the matter is densest. The pattern matches what we observe in the real universe. The simulations and reality agree, but we have never mapped the cosmic web in full. We have never had a telescope powerful enough to trace the dark matter filaments across the sky in high resolution. We know the web exists, we know its general shape, but we do not have a detailed picture. Rubin will change that. By measuring the shapes of billions of galaxies, scientists can detect the subtle distortions caused by gravitational lensing. Dark matter bends the light from distant galaxies ever so slightly. The effect is tiny for any single galaxy. But measure enough galaxies, billions of them, and you can reconstruct the shape of the invisible matter in between. This technique, called weak lensing, is one of the observatory's primary science goals. It requires enormous numbers of galaxies, observed with extreme precision across a wide area of sky. Previous surveys measured millions of galaxies. Rubin will measure billions. The leap in scale is enormous. For the first time, we will see the skeleton of the universe, the hidden framework that holds everything together, the structure that has been shaping the cosmos for billions of years, unseen. But mapping the web is only half the challenge. Understanding what is pulling it apart is the other half, and that mystery is far stranger than anything we have discussed so far. Something out there is working against the web, fighting against gravity, pushing the structure apart even as gravity tries to hold it together. Understanding what that force is and how it behaves is one of the most important challenges in all of science. And this telescope is one of our best chances to find answers. The web is real, the force working against it is real, and the battle between them is shaping the future of every galaxy in existence. Light travels in straight lines. That is one of the first things we learn about physics. But it is not entirely true. When light passes near something massive, its path curves. The more massive the object, the greater the bend. Einstein predicted this over 100 years ago. It was confirmed during a total eclipse in 1919, when starlight was seen bending around the edge of the blocked-out disk. The stars near the edge appeared to shift position. Space itself was warping near the massive body, and the light followed the curve. This effect is called gravitational lensing, and it does not require a visible object to cause the bend. Dark matter, invisible and untouchable, still has mass. It still warps space, and it still bends light. When a massive cluster of dark matter sits between us and a distant galaxy, the galaxy's light curves around the cluster. Sometimes the image is distorted into beautiful arcs. Sometimes it splits into multiple copies of the same galaxy, appearing in different positions around the cluster. In extreme cases, the galaxy's light is stretched into a complete ring, called an Einstein ring. These are among the most striking images in all of astronomy. These are dramatic examples of strong lensing. They are rare and visually stunning. But for mapping dark matter across the entire sky, scientists use a subtler version called weak lensing. In weak lensing, the distortion is so small that you cannot see it in any single galaxy. The shape change might be less than 1%. A galaxy that would look perfectly round might appear very slightly oval. You would never notice the difference by eye. But if you measure the shapes of millions or billions of galaxies, you can detect a statistical pattern. Galaxies in a particular region might all be slightly stretched in the same direction, pulled by the gravity of dark matter you cannot see. Rubin will observe billions of galaxies across the southern sky. Its sharp images and wide coverage make it the ideal machine for weak lensing studies. No other telescope can match both its depth and its breadth at the same time. Confirmed, the Vera Rubin Observatory was designed from the start to map dark matter using gravitational lensing of distant galaxies. The result will be a three-dimensional map of dark matter, showing where it clumps, where it thins, and how its distribution has changed over cosmic time. But understanding dark matter is only part of the question. Something else is at work, something that pushes where gravity should pull, and it might be the strangest force in nature. For decades, scientists have known that something is wrong with our picture of the cosmos. The visible matter does not add up. The equations do not balance. Something enormous is missing from the ledger. Rubin's map of dark matter will fill in the blanks, revealing the hidden mass that shapes everything we see, and what it shows may change everything. In 1998, two teams of astronomers made a discovery that shook the foundations of physics. They were studying distant supernovae, using their brightness to measure how far away they were and how fast the universe was expanding. They expected to find that the expansion was slowing down. Gravity, after all, pulls matter together. After the initial push of the Big Bang, the universe should have been decelerating. Like a ball thrown into the air, it should have been gradually losing speed. Instead, they found the opposite. The expansion was speeding up. Galaxies were moving apart faster and faster, as if something was pushing them. Something invisible, something immensely powerful, something that acted against gravity on the largest scales imaginable. They called it dark energy. And nobody knows what it is. Dark energy makes up roughly 68% of the total energy in the universe. It is not matter. It does not clump into structures. It does not interact with light. It simply drives the universe apart, and it has been doing so for billions of years. It fills all of space, uniformly, silently, relentlessly. Is it a property of space itself? A constant energy woven into the fabric of the cosmos, present even in the emptiest void? Or is it something that changes over time, growing stronger or weaker as the universe ages? Could it be a new field of energy that we have never detected directly? These are among the biggest open questions in all of science, and the Vera Rubin Observatory was built to help answer them. By observing billions of galaxies at different distances, which means different points in time, Rubin can measure how the expansion rate has changed across cosmic history. It can track the growth of large-scale structures. It can compare how galaxies cluster today versus how they clustered billions of years ago. If dark energy is constant, the measurements will fall along a predictable curve. If it is changing, the curve will bend in unexpected ways. Even a small deviation could rewrite our understanding of the cosmos. Theory. Some physicists believe dark energy could be a sign that our understanding of gravity itself needs to be revised at the largest scales. Unknown. Whether dark energy will eventually tear the universe apart entirely in an event sometimes called the Big Rip, where even atoms are pulled to pieces. The observatory's data will not answer everything, but it will narrow the possibilities dramatically. Closer to home, glittering trails of stars inside our own galaxy may be hiding secrets of their own. The answers to the biggest questions in physics might be written in the light of distant galaxies. We just need to gather enough of it, measure it precisely enough, compare it carefully enough, and then let the data speak. That is what this telescope was built to do. Listen to the light and hear what the universe is trying to tell us. The Milky Way is not alone. It has neighbors. Small, faint, dwarf galaxies orbit around it, held in place by gravity. Some of them are so dim they are barely visible even with powerful telescopes. They drift quietly in the darkness, circling our galaxy like moths around a lantern. Over billions of years, the Milky Way has been pulling these smaller galaxies apart. Stars that once belonged to a compact dwarf galaxy get stretched into long, thin streams like taffy being pulled. Slowly, orbit after orbit, the smaller galaxy loses its shape. Its stars spread out along the orbital path until all that remains is a faint ribbon of light arcing across the sky. These are called stellar streams, and they are some of the most beautiful structures in our galaxy. They curve across the heavens like rivers of light, tracing the path of the orbit of a galaxy that no longer exists. Each stream is a fossil record, a memory of something the Milky Way consumed long ago, a ghost of a galaxy, stretched thin and woven into our own. But stellar streams are more than just beautiful. They are tools, powerful scientific instruments hiding in plain sight. Because dark matter, even though it is invisible, interacts with streams through gravity. If a clump of dark matter passes near a stellar stream, it disrupts the flow. It creates a gap, a thin spot, a place where the stream is slightly broken. The stars get nudged. The ribbon develops holes. By studying these gaps, scientists can learn about the distribution and behavior of dark matter at very small scales, scales that other methods cannot reach. This is incredibly difficult to observe. The gaps are subtle, the streams are faint, You need a telescope that can see extremely dim objects across an enormous area of sky, with enough repeat visits to map every stream in detail. Rubin is that telescope. It will detect stellar streams at distances roughly 5 times farther than current telescopes can reach. It will reveal an entirely new population of streams in the outer regions of the Milky Way, streams that have never been seen before. Confirmed. Scientists are already preparing to use Rubin data to study how dark matter disrupts stellar streams. Every stream tells a story. Every gap in the stream is a clue. And together, they may reveal the hidden texture of the dark universe around us. But the secrets hiding in our neighborhood do not stop at stellar streams. There may be something much larger lurking at the edge of our solar system, something no one has ever seen directly. The Milky Way has been eating its neighbors for billions of years. It will continue long after we are gone. Every stream is evidence of that cosmic appetite. Every faint ribbon of light is a galaxy that lost the fight. And Rubin will find more of them than anyone thought possible. Each one a ghost, each one a story written in starlight. For years, astronomers have noticed something strange about the outer solar system. A group of distant objects beyond Neptune, in a region called the Kuiper Belt, seem to have orbits that are weirdly aligned. They cluster together in a way that should not happen by chance. Their paths through space lean in the same direction, as if something massive is pulling them. One explanation is that a large, unseen planet is out there, tugging on these objects with its gravity. It has been given the name Planet 9, and if it exists, it could be several times the mass of Earth, orbiting far beyond anything we have ever directly observed. It would be so distant that it takes thousands of years to complete a single orbit. Nobody has found it yet. No telescope has spotted it. Its predicted orbit places it so far from the center of our solar system that it would reflect almost no light. It would be incredibly faint, moving slowly against the background stars, easy to miss even in a deep survey. But the Vera Rubin Observatory has a chance. Its wide field of view, repeated observations, and sensitivity to faint objects make it one of the best tools available for this search. If Planet 9 is out there, and if it falls within the survey area, the telescope could detect it. Its motion, however slow, would show up across multiple images taken on different nights. The software would link those detections together and flag the moving object. Theory: Planet 9 was proposed in 2016 based on the clustering of distant Kuiper Belt objects. Some scientists believe it exists. Others think the clustering is a statistical coincidence, a trick of small sample sizes and observational bias. The debate remains open, unknown. If it exists, what is it made of? How did it get so far out? Was it formed in our solar system and flung outward by the gravity of the giant planets? Or was it captured from another system entirely, drifting through space until our gravity caught it? Even if Planet 9 does not exist, the search will not be wasted. The observatory will discover thousands of new Kuiper Belt objects regardless. Each one is a frozen relic from the earliest days of our solar system, a time capsule 4.5 billion years old. Some may contain water ice. Some may contain organic compounds. Each one is a window into how the planets formed. The outer solar system is one of the least explored regions of our cosmic neighborhood. This telescope will open a window into it that has never been available before. The numbers, when you hear them, are almost impossible to grasp. Whether Planet 9 exists or not, the outer solar system is about to become a lot less mysterious. Thousands of new objects will be catalogued. Their orbits will be mapped. Their compositions will be studied. And slowly, piece by piece, we will build a clearer picture of how our solar system formed and how it evolved over 4.5 billion years of cosmic history. Over the course of its 10-year survey, the Vera Rubin Observatory is expected to observe roughly 20 billion galaxies. That is more galaxies than there are people on Earth. Let that settle for a moment. More galaxies than every human being alive today. No telescope has ever come close to this number. Previous surveys catalogued millions, sometimes tens of millions. Rubin will catalogue billions. Each galaxy will be measured multiple times, in multiple filters, across multiple years. The depth of information for each one will be extraordinary. For each galaxy, the data will include its position, its brightness, its color, its shape, and how it changes over time. For many galaxies, scientists will also be able to estimate their distance using a technique based on how their light shifts toward the red end of the spectrum. The farther away a galaxy is, the faster it moves away from us, and the more its light stretches toward red. This catalogue will be the most comprehensive map of the observable universe ever assembled. It will allow scientists to study the distribution of matter at scales that have never been accessible before. Patterns that are invisible in small surveys will leap out of a dataset this large. Why does that matter? Because the way galaxies are distributed tells us about the physics that shaped the universe. Galaxies are not scattered randomly. They cluster along the filaments of the cosmic web, pulled together by gravity and dark matter. The spacing between clusters, the density of the filaments, the size of the voids, all of these carry information about how the universe evolved. By measuring how tightly galaxies cluster at different distances, and therefore at different points in cosmic history, scientists can test models of how the universe grew from a smooth, hot fog into the complex web of structures we see today. They can look for patterns that match predictions, or they can find anomalies that suggest something entirely new. Rubin will also observe roughly 17 billion stars within our own galaxy. Many of these will be variable stars, objects that change brightness over time. Some pulse like heartbeats. Some flare suddenly and unpredictably. Some are eclipsed by orbiting companions. Confirmed. The observatory will catalogue more objects than any project in the history of astronomy. Every number in that catalogue is a data point, and every data point is a potential discovery. But the most powerful feature of this survey is not any single image. It is the combination of all of them over 10 years. Imagine having a baby photo, a childhood photo, a teenage photo, and an adult photo of every galaxy in the sky. That is what this survey will provide. A biography of the cosmos, written in light, captured by the largest camera ever built, and stored forever in the archives of human knowledge. A 10-year movie of the universe. And what it might reveal could change everything. Most telescopes take snapshots. They photograph a piece of the sky, study it, and move on. Rubin will do something fundamentally different. It will build a time-lapse of the entire southern sky, a movie that runs for 10 years. And in that movie, the universe will come alive. Every 3 nights, the telescope completes a full sweep. By comparing each new sweep to the last, scientists can track how the sky changes. Stars that brighten and dim, galaxies that shift, new objects that appear, old objects that vanish, the cosmos in constant, restless motion. This is called time domain astronomy, and Rubin will be the most powerful time domain observatory in history. Think about what that means. If a star explodes in a distant galaxy, Rubin has images of that galaxy from before the explosion. It has images during, and it will have images after. Scientists can study the full life cycle of the event, from the quiet calm before the blast, through the violent peak, to the slow fade into silence. No other telescope has ever been able to do this at such a wide scale. If an asteroid changes its orbit slightly, perhaps after a close encounter with another body, Rubin will track the change over weeks and months. If a quasar flickers in a pattern that matches the passage of a hidden black hole, Rubin will record every flicker across a decade. If a new class of exploding star appears, one that nobody has ever documented, it will show up in the data, again and again. Over 10 years, The survey will visit each point on the sky roughly 800 times. Each visit produces data in one of 6 color filters. The result is not just a map, it is a living, breathing portrait of a universe in motion. And all of this data will be made available to scientists worldwide. 2 data centers, one in the United States at the Stanford Linear Accelerator Center in California, and one in France, will process and store the information. Regular data releases will allow the global community to dive in and make discoveries. Theory. Some scientists believe this dataset will lead to entirely new fields of astronomy that do not exist yet, fields we cannot even name today. The sheer volume of data means that no single team can analyze it all. The discoveries will come from everywhere, from universities, from amateur astronomers, from students writing their first research papers. And some of the most important discoveries might be things nobody predicted. Science has always worked this way. The tools reveal what the theories could not anticipate. The telescope does not follow instructions, it follows the light. And wherever the light leads, the data will follow. 10 years of watching, 10 years of recording, 10 years of building the most complete portrait of the cosmos ever assembled. And then the questions will come. Questions nobody has thought to ask yet. Every great telescope in history has found things nobody expected. The Hubble Space Telescope was built to measure the expansion rate of the universe. It did that. But it also revealed that nearly every galaxy has a supermassive black hole at its center. It showed us galaxies at the edge of the observable universe. It gave us the deep field images that became icons of science. The James Webb Space Telescope was designed to see the earliest galaxies. It did, but it also found galaxies forming far earlier than anyone thought possible, challenging models of how the universe evolved. It found things the theorists had not predicted. It broke expectations. Rubin will follow this pattern. It was designed for specific goals: dark matter, dark energy, asteroids, transients. But its greatest discoveries will almost certainly be things nobody imagined. When you photograph the entire sky every 3 nights for 10 years, you create a dataset so vast that patterns will emerge that no one was looking for. Correlations between objects that seem unrelated, behaviors that repeat in ways that match no known model, anomalies that defy explanation. Some of these might be new types of stellar explosions that do not fit into any existing category. Some might be gravitational wave events detected in light for the first time, allowing scientists to study the collision from multiple angles simultaneously. Some might be entirely new classes of objects that we do not have names for yet. This has happened before. Pulsars were discovered by accident in 1967 by a graduate student named Jocelyn Bell Burnell. She noticed a repeating signal in radio data that nobody could explain. It turned out to be a rapidly spinning neutron star, sending out beams of radiation like a lighthouse. Nobody was looking for it. Nobody predicted it. But there it was. The history of astronomy tells us that the most transformative discoveries often come from instruments that see the sky in a new way, a wider view, a deeper view, a faster view. Rubin sees the sky wider, faster, deeper, and more repeatedly than anything before it. The conditions for surprise are perfect, unknown. What surprises are waiting in a dataset of 20 billion galaxies observed 800 times each? The telescope does not care about our predictions. It will record what is there, and whatever it finds, it will share with the world. That process of sharing happens faster than you might think. Every single night, the telescope speaks. It sends its data down the mountain, across the ocean, and into the waiting servers. It flags the changes, it catalogues the discoveries, and it waits for us to ask the right questions. The universe has been keeping secrets for nearly 14 billion years. And now, for the first time, we have built something patient enough, powerful enough, and fast enough to start uncovering them. One night at a time, one image at a time, one alert at a time. Within 60 seconds of detecting something unusual, the Vera Rubin Observatory will send an alert to astronomers around the world, not in an email, not in a weekly report, in real time. As fast as the data can travel from a mountaintop in Chile to a laptop in Tokyo or a control room in London. Every night, the system will generate roughly 100,000 alerts. Each one signals that something in the sky has changed. A new dot of light, a brightening star, a moving object, a sudden flash that was not there 3 nights ago. These alerts will flow into a global network of astronomers, observatories, and automated systems. Some will trigger follow-up observations at other telescopes within minutes. A burst of light detected in Chile might prompt a radio telescope in Australia, an X-ray satellite in orbit, and an optical telescope in Hawaii to all point at the same spot simultaneously. The universe speaks in many wavelengths. To hear the full message, you need many ears listening at once. This is the new era of multi-messenger astronomy. Instead of one telescope studying one event in one type of light, entire networks respond to discoveries in real time across all wavelengths. Light, radio waves, X-rays, gravitational waves, all captured together, all analyzed together, a single event studied from every possible angle. Rubin is designed to be the trigger, the first detector, the alarm bell. It spots the change and tells the world. Other telescopes then rush in to study the event in detail, each one adding a new layer of understanding. Consider what happens when 2 neutron stars collide. The event produces gravitational waves, gamma rays, ultraviolet light, visible light, and radio waves, all within seconds or days of each other. Catching all of those signals requires coordination across dozens of instruments on multiple continents and in orbit. Missing even one signal means losing part of the story. The observatory's wide field coverage means it has one of the best chances of catching the optical flash from such an event. Its alert system means the rest of the world knows within a minute. Confirmed, this alert infrastructure is being built and tested now, in preparation for the survey start in early 2026. The speed of discovery is what sets this telescope apart. It does not just observe the universe, it responds to it, in real time, every single night. And all of this data, every alert, every image, every catalogue, will eventually be available to everyone, not locked away in a vault, not reserved for a select few, shared with the world. The universe sends us signals every second of every day. Most of them pass unnoticed. Most of them are never recorded. But for the next 10 years, this telescope will catch as many of them as it possibly can, and it will pass every single one along to anyone willing to listen. The age of cosmic surveillance has begun. One of the most remarkable things about the Vera Rubin Observatory is that its data will not be locked behind laboratory doors. It will be shared, widely, with scientists first, and then with the entire world. After processing, the observatory's data will be released to the scientific community and, over time, to the public. Anyone with an internet connection will be able to explore the most detailed map of the universe ever made. You will not need a degree. You will not need special software. You will just need curiosity. Plans are already in place to build interactive tools that let people fly through 3-dimensional reconstructions of the cosmos. Think of it like a search engine for the sky. You could zoom into a galaxy, track an asteroid as it moves across weeks of observations, or watch a star pulse over years of recorded data. The universe, in your hands, on your screen. This is possible because of the massive computing infrastructure behind the project. 2 data centers, one at the Stanford Linear Accelerator Center in California and one in France, will process and store petabytes of data. Automated software will classify objects, flag changes, and build catalogs that scientists and the public can search. Citizen science projects may also emerge, where volunteers help identify unusual objects in the data. This has been hugely successful with past telescopes. The Galaxy Zoo project, for example, relied on hundreds of thousands of volunteers to classify galaxy shapes. Volunteers discovered new types of galaxies, unusual formations, and objects that professional astronomers had missed. With 20 billion galaxies in the catalogue, this observatory's dataset will need all the help it can get. Every night, the telescope generates about 20 terabytes of new data. Over 10 years, the total will dwarf the combined archives of every previous astronomical survey ever conducted. It will be the single largest collection of astronomical observations in the history of our species. Theory. This open data model could become a template for future large-scale science projects, showing that the best discoveries happen when data is shared freely. The universe does not belong to scientists. It does not belong to governments or institutions. It belongs to everyone. And for the first time in history, a telescope will deliver the visible cosmos directly into the hands of anyone who wants to explore it. But what does all of this mean? What is the real legacy of this telescope and the woman it is named after? That answer reaches far beyond the stars. For centuries, the sky was the province of the few. Only those with access to expensive equipment and elite institutions could study the cosmos in detail. The rest of humanity could only look up and wonder. This telescope changes that. It brings the universe to everyone. It takes the most ambitious scientific project in the history of astronomy and opens its doors to the world, and that may be its greatest legacy of all. Vera Rubin spent her life looking at what others had overlooked. She studied the edges of galaxies when everyone else focused on the centers. She collected data patiently, carefully, when others dismissed her work. She fought to be in rooms where women were not welcome, and she found something that changed the course of science forever. She once said, "There is no problem in science that can be solved by a man that cannot be solved by a woman." She proved that with her life. Every barrier that was placed in front of her, she climbed over, walked around, or pushed through. And she did it while raising 4 children, all of whom went on to earn doctoral degrees in science and mathematics. The telescope that carries her name is not just a machine. It is a continuation of her curiosity. It asks the same question she asked decades ago, staring at the strange rotation curves of galaxies late at night in an Arizona observatory. What is hiding in the dark? Over the next 10 years, the Vera Rubin Observatory will photograph the entire southern sky more than 800 times. It will catalogue 20 billion galaxies. It will discover millions of asteroids. It will catch exploding stars in the act. It will map dark matter across billions of light years. It will probe dark energy. And it will find things that nobody has predicted, things that will surprise us, things that will challenge us, things that will rewrite textbooks. Confirmed, the Legacy Survey of Space and Time is expected to begin in early 2026. The telescope is ready. The camera is in place. The mirrors are aligned. The software is running. The mountain is quiet. And the sky is waiting. The most ambitious astronomical survey in human history is about to start. And somewhere, in the flood of data that will flow down the mountain every night, there will be answers to questions Vera Rubin asked 50 years ago, answers she never got to see, answers that were hiding in the dark, waiting for the right eyes to find them. This telescope is her legacy, and it is only the beginning. Thank you for staying through this journey. We traveled from a bedroom window in Washington, where a young girl sketched stars, to a mountaintop in Chile, where the largest camera ever built is opening its eye to the cosmos. The universe is vast, it is mostly dark, and it is full of secrets. We are watching back, and who knows? Maybe somewhere in those 20 billion galaxies, in a corner of the sky nobody has looked at yet, there is something waiting to be found. Something that will change everything. Something that will make us rethink what we thought we knew. Vera Rubin would have liked that. She always said the best discoveries come from looking where nobody else does. The telescope is ready, the sky is open, and the watching has begun.